Greetings, fellow do-it-yourselfers. In this special video, I am going to reveal my deepest secret, and that is the understanding of fuel trims. And you will need a scan tool for this. However, you can use even the most basic of scan tools. Nowadays, there's $100 scan tools from Actron available that you can easily get. And you need one that will have fuel trim data, short-term and long-term fuel trim data, and preferably oxygen sensor data. And the idea is, if you master the concepts that I will show you in this video about fuel trims, you will absolutely dramatically improve your diagnostic capability far beyond that of your average weekend warrior or shade tree mechanic. And to be honest with you, even past a lot of professional mechanics, to be honest. So let's go ahead and start from the beginning and talk about fuel induction, computerized fuel control. You have to understand that to then understand fuel trim. Once you understand fuel trim, you will be able to actually think like the engine computer, if not the engine itself, and therefore, given certain responses that the engine has to different stimuli or different inputs that you give it, you will be able to very much determine a good direction. It's a very, very powerful ability to have. So if you're the type of person that likes to replace all kinds of parts and get all dirty and everything and use every wrench in your toolbox, this will not be the video for you. For you guys, AutoZone is open till 9. Believe me, they love you. For the rest of you that want to be able to get an absolute accurate diagnosis, or at least an accurate direction on where to go on most check engine light problems, then you're going to have to master these concepts. So let's take a look. All right, and yes, we are going to use my amazing artistic abilities in this exercise, but let's start off here. We've got an engine here, and of course we've got air that comes into the engine. We have fuel delivered into the engine, and of course we have an exhaust with a usually an oxygen sensor. We'll label that O2. And I am well aware that most new engines don't use oxygen sensors now. They have these things called air fuel sensors. And if you're familiar with oxygen sensors, the first time you run into an air fuel sensor, it's a pretty interesting experience and probably an expensive one, because you're going to almost certainly think you have to replace a non-responsive oxygen sensor. O2 sensors and air fuel sensors, or wideband oxygen sensors, are completely different things. I'm going to actually do a video on that soon to explain those. But know that for the concept of fuel trims, which is the purpose of this video, the concept of fuel trims is identical whether your car uses an O2 sensor or an air fuel sensor. So that part won't really matter as much. The concept of fuel trims is identical either way. Now, we're going to go ahead and use oxygen sensor in these examples simply because I want you to master the concept of fuel trims. And if you, most likely, if you're watching my videos, you're more familiar with oxygen sensors. So we're going to use that as an example, but it really doesn't matter for fuel trims. So in your engine, of course, you've got the air coming in. It mixes with fuel in a combustion chamber. It blows up and then comes out as exhaust, and the oxygen in the exhaust measured by an O2 sensor. Now, the important thing to know in a computerized engine is that the computer is very, very, very particular about this air-fuel mixture. And that air-fuel mixture is always, well, not always, but always going to have to be what's called a stoichiometric ratio, or in stoichiometry. And that's going to be 14.7 parts air to 1 part fuel. And the computer is going to be very, very obsessive compulsive about this. There's only a couple times that the computer will not have that mixture. That would be on a cold engine startup. You need a richer engine for better startup. Wide open throttle is another example, but there are some exceptions to this rule. But in general, keep in mind, computer is obsessive compulsive. It is always going to try to make a 14.7 to 1 stoichiometric mix. Now, the question is, how does the computer do that? How does it know? Well, it's not from the oxygen sensor, actually. It's because with this air coming in, there are going to be various input sensors to detect the amount of air coming in. In many engines, there's going to be a MAF, or a mass airflow sensor. Also keep in mind that the temperature of the air has an effect. Colder air is more dense, so there's going to be some type of intake air temperature sensor to tell the temperature of the air. Many engines also have on the intake a manifold air pressure, or a MAP sensor. And given all of these inputs here, the computer knows how much air is coming into the engine. If the computer knows how much air is coming to the engine, then it knows how much fuel to add to stay in stoichiometry. And it, of course, adjusts the fuel by regulating the pulse width on the fuel injectors. Now, after the combustion, the oxygen in the exhaust is measured by the O2 sensor. And part of the responsibility for the O2 sensor, it's got two responsibilities. One of them is to maintain optimal activity of the catalytic converter, and the other one is to adjust the amount of fuel necessary if the combustion didn't exactly go as planned. In other words, a fuel trim. It trims the amount of fuel added to compensate for any error from these sensors, or more likely from any unmetered air, any air that entered the engine that wasn't measured by these sensors, a vacuum leak, or by some type of fuel delivery problem, leaking fuel injector, something like that. So let's go ahead and look at this in a little more detail, because we need to understand how the computer uses this oxygen sensor to tell whether there needs to be some adjustment to the fuel. So we have our air coming in mixed with our fuel, and of course it combusts, and the combustion is sort of validated by the O2 sensor. Now, if you're familiar with an O2 sensor, you know that it has a waveform to it like this, from 900 millivolts to 100 millivolts. An oxygen sensor is basically a battery that wants to emit about a volt. And in the presence of oxygen, however, that voltage is inhibited. So if there is oxygen present in the exhaust, in other words, a leaner exhaust, then the voltage is going to be at the lower end of the scale. And if there's very little oxygen at all in the exhaust, then that's a richer exhaust, and the O2 sensor can emit maximum voltage. But this doesn't make much sense at this point, because if we think about it, if the computer is trying to maintain a perfect stoichiometric ratio, then the oxygen sensor should be flatlined at 0.45 volts, correct? Correct. That actually is right. So in your ideal situation, this is what you would have. Now the problem is that a catalytic converter is not able to optimally clear pollutants in this condition. A catalytic converter can clear some pollutants when there's a little bit of a richer condition and increasing the temperature, and then there is other pollutants that the catalytic converter is better at with a leaner condition. So the computer is going to actually control fuel delivery to oscillate between, actually let's make a dotted line at 0.45 volts. But the computer, and here's 900 millivolts and 100, the computer is going to oscillate between that lean and rich condition, and that's why you get this waveform. However, if the engine is at stoichiometry, there will be a center line between those sine waves at 0.45 volts. So that's why you have that oscillation with the oxygen sensor. Now, there is our perfect world, right? Very simple. Computer knows how much air is coming in. It knows exactly how much fuel to deliver. The computer oscillates a little bit rich, a little bit lean. The oxygen sensor responds to that with this wave. The computer sees that wave is optimal. Perfect world. What is there to worry about? Well, the problem is this assumes that the engine is absolutely accurate at measuring how much fuel and air is being mixed. It knows exactly how much air is coming in. What happens as the engine ages, or if the spark isn't quite as much, or there's a variance in fuel pressure, or there is a little bit of a vacuum leak. So more air comes in, but this air from the vacuum leak is not measured by any of the MAP or MAF or IAT. Well, then that creates a problem for this system, because now, since the amount of extra air from this vacuum leak coming in is not measured, that is not going to be compensated for by the fuel in the engine, and therefore the exhaust is going to be lean, and that is going to start creating a response in the oxygen sensor where it starts leaning out, and that is not good, and the computer does not like that. Enter fuel trims to correct this condition. So let's take a look at that. All right, now keep in mind that oxygen sensors aren't even functional until they get up to 700 degrees or so. So when examining fuel trims and doing the things I'm going to show you, make sure that the engine is warmed up. Again, at cold start, the engine needs to be rich anyway, but it doesn't matter. The oxygen sensors won't even be functional. But let's take a look at fuel trim. Let's go ahead, and we've got our engine, and we've got our intake here with, of course, let's put a MAF sensor on here, and then maybe there's also a MAP over here, and of course we're going to have here an intake air temp. So this engine has all of these inputs to measure that amount of air coming in. The engine knows how much air is coming in, all right? But we've got a little bit of a problem. Right here is an intake leak. So we have some unmetered air coming in through this leak. All right? And then, of course, what's going to happen is the exhaust is going to be leaner, and that's going to be detected, of course, by the O2 with a lean trace. The computer does not like that. What the computer is going to do is it is going to see this, and the computer is going to say, there must be some other source of air coming in. I don't care. I don't know where it's from. I don't know what's wrong. Maybe it's also because there's just not enough fuel delivery. Who knows? Who cares? All I know is we are not at 14.7 to 1. We need more fuel to bring this back up to stoichiometry. And the computer will do that using short-term fuel trim, or STFT, as you will see on your scan tool. And what you will see in this case is a couple things. If we look over time at your short-term fuel trim, it is going to be shown as a percent. And the way to think of fuel trims is as kind of a percent deviation from normal that is required by the computer with the addition of fuel to maintain stoichiometric ratio. So in this case, what's going to happen is your short-term fuel, which would normally be at 0 with the vacuum leak, your short-term fuel trim is going to increase. It's going to start going positive. And these numbers can be anywhere from 50 to -50 to 100. Whenever you see your short-term fuel trim or long-term fuel trim, which I'll talk about, going positive, that is a response to a lean condition. Conversely, if you see the fuel trims going negative, that's a response to a rich condition, and that's going to tell the computer to reduce injector pulse length and reduce the amount of fuel delivery. In this case, with a vacuum leak with unmetered air entered, we would see the short-term fuel trim increase. It's kind of the equivalent of adjusting a carburetor for a lean condition, sort of by adding more fuel. That's what's happening here. What we would see with the oxygen sensor is, of course, the oxygen sensor would be normal. With the induction of a vacuum leak, we would see it lean out. But then as this short-term fuel trim increases, it's going to add more and more fuel until we get back to normal. Once that happens, that short-term fuel trim is going to level off. And it's going to remember that setting for this condition on the percentage of fuel that was necessary to add to return a stoichiometric ratio. And that level that the short term is at is going to be memorized. It is going to be learned by the computer as long-term fuel trim. And what the long-term fuel trim is that sets a new 0 point for the fuel delivery. Let's say it's at 25% more fuel in this case. And the computer is going to remember that, so the engine is by default going to add 25% more fuel until the condition is fixed. So let's take a closer look at that. So here we've got two graphs. We've got short-term fuel trim on top and long-term on the bottom. And let's put 0, 25, and minus 25. And the same thing here, 0, 25, and minus 25. And let's say we've got a brand new engine and everything's all great. So short-term fuel trim is going to be at around 0. Long-term fuel trim is going to be at around 0. Down here is your O2 sensor trace. O2 sensor trace looks great. Everybody's happy, right? Then let's say we pull a vacuum line. Well, when we pull the vacuum line, O2 sensor is going to detect that extra lean exhaust that we create because the computer doesn't know we pulled the vacuum line. It has no idea. The oxygen sensor does detect it though, so it's going to go lean out. Remember, lower voltage, it's detecting lean. Once that happens, short-term fuel trim is going to respond immediately. A short-term fuel trim is an immediate response, and it's going to start going positive, adding fuel until the oxygen sensor starts to respond a little bit. And the computer is going to keep adding, and let's say in this case it's up to 20%. Generally you'll get a check engine light at about 20 to 25% on most vehicles, usually 25% or more. And it's going to be a code for a lean condition. We'll talk about that. Now, this whole time that this is happening, this long-term fuel trim is going to start going, well, we better start paying attention to what this guy's doing. So he's going to be a little slow because he's a learned response, but eventually that's going to start pulling up. Now, once enough fuel is added where the O2 sensor returns to normal and the computer sees, good, we're back at stoichiometry, that percentage, 20%, is going to be memorized by the long-term fuel trim, and that sets the new baseline. But that means we no longer have to call for the addition of fuel from the short-term fuel trim because the long-term fuel trim has now set that 20% extra fuel as the new baseline. So we're going to see the short-term fuel trim start coming down back to 0. And of course the oxygen sensor continues on its happy, merry way. So the thing is there is still something wrong with this car. Even though the short-term fuel trim is at 0 and the O2 sensor looks great, we're still adding, by default, 20% more fuel to compensate for that vacuum leak that we caused. So that's the new baseline, and that's not a normal condition. But the engine will run perfectly fine. Now, let's do this. Let's go back just a little bit. And we've got our long-term fuel trim establishing that new baseline, so our short-term returns to 0, and we plug that vacuum line back in. What's going to happen? Well, at that point, because we're at a new baseline and there's no adjustment to the fuel delivery from the short term, what's going to happen is when we plug that line in, we're going to immediately have a rich condition. Why? Because the computer's adding 20% more fuel by default because of the new baseline set by the long term. If we go into a rich condition, what's going to happen is that short-term trim is going to start to go negative. It's going to call for the reduction of fuel because the oxygen sensor, when we plug that in, is going to start going rich. And the short-term trim is going to start going down to actually minus 20%. The long-term trim, again, slower to respond, is a learned response, and it's going to start going down. Now, eventually, we're going to reduce the amount of fuel till the O2 sensors return to normal because we're back at stoichiometry. That means that this new learned response, which in this case happens to be back at factory setting, 0% long-term fuel trim, and then of course the short-term fuel trim will level off back to 0 again. So that's how the responses of short-term and long-term fuel trim are tied in with the oxygen sensor. Great. How do we use this now to make diagnoses? Well, we're going to give some examples of it, and as a matter of fact, the diagnoses can get pretty sophisticated if you really look at this. So let's give a actual example of how you would use this knowledge now to determine the cause of a check engine light, a very common one. Let's do a P0171. And I hope I got this code right. An 0171, this is going to be bank 1 lean. In these examples right now, we're going to do 4-cylinder engines, and that was also assumed before in my explanations. With V engines, there's actually short and long-term fuel trim for each bank. And we'll get into that. As a matter of fact, it's actually easier to make a diagnosis on a V engine using fuel trims. We'll explain why later. But in this example, we've got a 4-banger with a P0171. That's going to read something to the effect of oxygen sensor, lean, bank 1, something like that. Of course, now to you realize what that means is the oxygen sensor is reporting a lean condition, and therefore the long-term fuel trim must be high enough that it set this code. That's for you, of course. For your parts changer or your typical AutoZone guy, the code means blah, 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 oxygen sensor, blah, blah, blah. You must need a new oxygen sensor. We know now not to put an oxygen sensor in this car based on if we see the normal oxygen sensor trace and a short-term fuel trim at 0, right? So let's look at this engine here. We've got your throttle here, so air is coming in here, but we have a little vacuum leak. Not a big one, just a little one, but enough that it sets this lean code. So we plug in our scanner and we've got a P0171. So we are going to go ahead, and what's the first thing we're going to do? Well, let's validate that code. Let's look at the long-term fuel trim. And we see our long-term fuel trim is at 25%. Now, what is the short-term fuel trim going to be without even looking? Well, almost certainly the short-term fuel trim is going to be around 0%. Because remember, the long-term fuel trim has set a new baseline, so there's no longer the need for the short-term trim to call for fuel. And we know our oxygen sensor should look like that. If we have these conditions and you put an oxygen sensor in this car to fix it, you're an idiot. Now, let's take a really close look at this, because one of the things is, remember, we don't know that there is a vacuum leak in this engine. All we know by looking at the long-term fuel trim is the engine's running lean. What other things could cause this? Couldn't a dirty mass airflow sensor cause it? Of course. Could a weak fuel pump not delivering enough fuel causing a lean condition cause this? Absolutely it could. So how would we know that we have a vacuum leak based on this? The answer is by thinking like the computer. How would it respond if this were a vacuum leak, and how can we simulate that to see if the responses are consistent with a vacuum leak? So let's think and use our brains really quickly here. We've got a little vacuum leak. So we do have some unmetered air coming into the engine. And all of this air here, of course, is metered air that's coming in through the sensors. If the engine is at idle, there's fairly little air coming in through the throttle. So the vacuum leak plays a fairly significant role in contributing unmetered air to the total amount of air in the engine. Now, let's say that we open the throttle plates and we get way more air coming into the engine. We increase the engine RPM, or you could see on your scan tool an increase in the throttle position sensor, however it is, and we bring way more metered air into the engine. Well, now this vacuum leak plays a smaller and smaller and smaller percentage of the total air in the engine, which means that less fuel trim is required to compensate for this. So let's look at that on a graph. So again, we're idling the engine and we've got our long-term fuel trim at 25%. But let's add in RPM. And here our RPM is low, but then let's say we increase the RPM and then tail off. If this were a vacuum leak, as we increase the RPM, as I said before, much more air is coming into the engine. So that vacuum leak becomes less and less significant, which means less fuel trim is required. So the short-term fuel trim, as you increase the RPM, is going to decline. It's going to pull this long-term fuel trim down, and we're going to see an improvement in the long-term fuel trim the more that we increase RPM. And we may even see at full RPM that our fuel trim might even be at 0. All right. Then as we let off the throttle and return back to idle, we see that again at idle, we're back. So if we see this pattern, we can pretty safely assume that a vacuum leak is the most likely cause. We should turn our direction to a vacuum leak. What's a good way to detect the vacuum leak? Well, one way I do it is my scanner to short-term fuel trim. What's the short-term fuel trim going to be? Well, it's going to be at 0. But then if I take propane and spray it around the engine, and we're going to see that short-term fuel trim immediately take a nosedive as soon as that propane gets sucked into the engine through that part that's leaking. So that's a great way to use your short-term fuel trim to detect where the leak is. Some shops may have some more fancy equipment like smoke machines and things like that. You could also use carburetor cleaner, any of those tricks. But if you set your short-term fuel trim on your scan tool, you can get an instant response when you catch where that vacuum leak is, because you're going to see the computer respond to that rich condition that you're creating using the propane or whatever.